Hi, everybody. So let's talk about some um, housekeeping. First of all, is that we have an exam this. Yeah, okay. So first of all, let's talk about some housekeeping. We have an exam this Friday, and I put the study guide telling you what you're supposed to know and what you're supposed to be able to do. I put that on the course website. I also put some instructions about how you're going to take the exam, how you're going to submit the exam, and so on. So is there any questions about all of the arrangements that we have made for this Friday's exam? Maybe you can unmute yourself and ask a question. Any questions about anything?
Will we still have lecture that day, or it's just a test? Is that my internet connection?
Well, you know what? It's funny you should say that, because didn't we miss a lecture because of a snow day or something earlier in the semester? So we need to make up one lecture. Right now, we are totally on track. So I don't see the necessity of having a lecture on Friday right now. But if I get behind, we're going to have a makeup lecture at some point. So I guess the answer to your question is this Friday, I'm not planning to have an exam. I'm not planning to have a lecture. I'm planning to have an exam.
Okay, thank you.
Anything else? Okay. So last time we were talking about the carbohydrates, and we mentioned that in solution, a carbohydrate exists as a 5 or a 6-membered ring cyclic hemiacetal. And these are called furanoses if they are 5-membered rings, and pyranoses if they are 6-membered rings. Okay, so today I want to finish up the material for the exam by talking about sugar acetals. We were talking about hemiacetals, and we know that if we have an excess of alcohol, the hemiacetal goes on to react to form the full acetal. So I want to apply that chemistry to the chemistry of the carbohydrates, and then that is going to bring our exam material to a close. Okay, so just to review the hemiacetal to acetal conversion, let's review that for a little while. So you have could have a sugar, a carbohydrate. Remember, that's a polyhydroxyaldehyde or ketone. And so so we have something like this. So that's not a carbohydrate yet because it's not polyhydroxy, but now we can put another OH group. Okay, and so now that is finally a sugar. And we made the point that in solution, this is the open chain form in solution, the hemiacetal, the open chain sugar, hooks up into a 5-membered ring or a 6-membered ring, hemiacetal. And this can happen under basic conditions or acidic conditions. And so this is going to ring up to a 1, 2, 3, 4, 5-membered ring, hemiacetal. So that's the hemiacetal. And we don't have time to talk about the mechanism of how that happens, but that's one of the things that you want to be able to master and be able to reproduce. Okay, now if there is more alcohol present the hemiacetal is going to go on to form the full acetal. So let's just put in here a simple alcohol such as methanol. And this is going to go on to form the full acetal. Okay, and that's the acetal. Okay, now when the acetal is derived from a sugar, as this guy is, it gets a special name. It's called a glycoside. Glyco means that came from a sugar, and the side means it's an acetal. Okay, and there are special names for the 5-membered ring glycoside and for the 6-membered ring glycoside. So this guy here that I've written here, this is a 5-membered ring. It's called a furanoside. Okay, and it's important to keep these vocabulary words straight because we talked about a furanose. A furanose is a hemiacetal. But the acetal is called, when it's a 5-membered ring, a furanoside. So this part means it's a 5 ring, and this part means it's an acetal. Just like with a furanose, the furan means it's a 5-membered ring, the ose means it's a hemiacetal. If it's a 6-membered ring, then it's called a pyranoside. And once again, this pyran means a 6-membered ring, and the side means it's an acetal. Okay, so it's important to keep these, they sound alike. Sorry about that, they sound alike, but it's important to keep these words straight. The furanose, that's the hemiacetal. The furanoside, that's the acetal. Pyranose and pyranoside. Okay, so let's leave this overall reaction up here and let's go through the mechanism just to review how the acetal forms from the hemiacetal. Okay, so eventually I'm going to work my way back to here, but I'm going to start over here. I want to review the mechanism of hemiacetal to acetal conversion. Okay, first step, I'm going to go way over here because I'm going to need a lot of room. First step is going to be the protonation of that OH oxygen. So this hemiacetal oxygen has unshared electron pairs on it. It is functioning as a base. It is picking up a proton from the solution. We could also, and remember, acetals only form in acid. So the first step will be the protonation of that OH oxygen to form this oxonium ion. Okay, and what we see here is these are the elements of water. Now they function as a leaving group. This carbon-oxygen bond breaks. Those electrons are ripped away by that oxygen atom as it leaves. Oxygen is highly electronegative. It doesn't like to have a positive charge. It would rather be neutral or negative. So this is its way of becoming neutral. So that goes off, minus H2O, that goes off into the solution. And what is left behind is this carbocation. What's left behind is this carbocation. This is the electrophile. It has a positive charge on this carbon. And now the second molecule of this alcohol now gets into the act. And the alcoholic oxygen has unshared pairs of electrons on it. The oxygen is the nucleophile. It attacks the electrophile. Okay, but now we have to take a little pause here because this alcohol can attack this positive charge from both above and below the plane of this carbocation. So just like we saw with the furanoses and the pyranoses, we're going to get alpha glycosides, alpha furanosides, alpha pyranosides, and beta glycosides, beta furanosides, and beta pyranosides, and beta pyranosides. Okay, so let's say that this oxygen attacked from the front. So the oxygen attacked from the front. And we got this dash, 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 positive charge on this oxygen. And then this alcohol could also have attacked from the back. So I'm going to try to fit that all in here. With a positive charge on this oxygen. Okay, and then the last step of the mechanism is once again we see that positively charged oxygen. We see that positively charged oxygen. The oxygen doesn't like to have a positive charge. It's going to want to become neutral, so that it does that by losing this proton. Something in the solution, water or some other kind of base, comes along and rips this proton off, and the oxygen atom gobbles up this electron pair. Something in solution comes along and the oxygen atom gobbles up this electron pair. And so this plus this, they get together and they form the acetal. Okay, so now I want to change, so that's the mechanism for the formation of the acetal, of the sugar acetal, of the glycoside from the sugar hemiacetal. Okay, minus H plus. All right, so last time we were talking about alpha and beta, and last time we were talking about D and L. All right, so I'm going to erase all of this stuff. Erase the mechanism. And now I want to make some further points about the stereochemistry. Whenever we're dealing with sugars, it's a whole lot of writing. There's because there are a lot of OH groups, and there are a lot of stereochemistry and a lot of the carbons. There's a whole lot of writing whenever we're talking about a carbohydrate. So to speed things along, to make our work a little bit shorter, when we want to communicate that both alpha and beta diastereomers were formed at this hemiacetal, or in this case acetal carbon, instead of writing the whole structure over and over and over again, what we do is that we can use a wavy line, and that means both alpha and beta. So this thing, same as, it cuts our work down a little bit, not a whole lot, but I guess anything is a savings. So we could write something that looks like this: wavy, 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 OCH3 plus. So what this wavy line, what this wavy bond is saying is that, well, we got this OCH3 group with a positively charged oxygen. It's both on a, some of the molecules have the OH on a wedge, some of them have it on a dash. This is just a conventional way, so we don't have to keep writing both the alpha and the beta over and over and over. Okay, so let's, just for practice, this is for fun and practice, let's look at the two glycosides here and just review whether they are D sugars, whether they belong to the D or L stereochemical family, and whether we have, and which one of these is the alpha glycoside and which one is the beta glycoside. Okay, so let's rewrite this. OCH3 dash 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 and OCH3 wedge wedge wedge. Okay, so this guy lost a proton, it became that. This guy lost this proton, it became that. Okay, so now tell me, do these glycosides belong to the D or to the L stereochemical family? So do you remember how to do that? The D stereochemical family has the R absolute configuration at the highest numbered chirality center, right? We begin at we give the acetal or the hemiacetal carbon the lowest possible number, but we have to start numbering from the end of the chain of carbon atoms. And we're numbering carbon atoms, and the chain cannot be interrupted by any other kind of atom. So that that's a carbon atom, but this would never be one because the next carbon atom is interrupted by this oxygen. That's carbon 1. We give the lowest possible number to the hemiacetal or acetal carbon, and carbon 2 is going to be not here because we can't interrupt the chain of carbon atoms with any other kind of atom. Carbon 2 is going to be here, carbon 3 is here, carbon here is 4. So the D stereochemical family has the R absolute configuration at the highest numbered chirality center. So carbon 3 is the highest numbered chirality center. Tell me, just work on this on your own. Is it the D or the L?
The L.
Okay, the absolute configuration here is this is going to be 1. Oh, tied. Go to the next atom. That's an oxygen, that's a carbon. Oxygen wins. So it's 1, 2, 3. That's a clockwise sweep, but remember the hydrogen here is pointing at you on a wedge. You're looking at the molecule backwards. Reverse it for the correct answer. This is an S absolute configuration. Whoa. And so this is an L sugar. So good, whoever said that. I heard someone say L. Good. All right, and this is going to be the very same thing. This is also an L stereochemical family. Okay, and so now is it which one of these is the alpha glycoside? Which one of these is the alpha furanoside, and which one is the beta furanoside? So do you remember how to do that? Okay, so if the acetal or hemiacetal carbon has the same absolute configuration as the highest numbered chirality center, that is beta. Same has 4 letters, so does beta. That's the cheesy way I remember it. If the highest numbered chirality center and the hemiacetal or acetal carbon have different absolute configurations, one is R and one is S, that's the alpha. Okay, so tell me, which one of these is the alpha and which one of these is the beta? So this guy is S. Are you working on that? Which one is the alpha and which one is the beta? Okay. What's that?
Alpha's on the right.
Alpha's on the right, someone says. Okay. So here we have, it's an, what's the absolute configuration configuration here. That's an oxygen, that's an oxygen. Tied, go to the next set of atoms. This one is CHH. Go to the next set of atoms, that's a carbon, and that's a carbon. His next set of atoms is CHH. This next set of atoms is HHH. So this guy, this road one. 1, 2, 3. That's an R absolute configuration, is it not? Yeah, it is. So this one has the opposite pattern of dashing and wedging, so that's the S absolute configuration. So I'm getting that these guys have the same absolute configuration, right? Let's see, 1, 2, 3. Yeah, these guys have the same absolute configuration. So this is the beta. These guys have different absolute configurations. So this one is the alpha. Okay, and then we could keep going with the name here. We could say that this is an L-alpha furanoside. And this is an L-beta furanoside. Right? And then there are even names, which we're not going to get into, about depending on what the sugar is, that is going to have a name as well. Like, for example, if it's glucose, that's the sugar. If it's glucose, this would be called a glucofuranoside. If it's fructose, let's say that's the parent sugar, this would be a fructofuranoside, and so on and so forth. But we don't have to get into any of those names. Okay, so that's so we have this very same system of nomenclature with the sugar acetals that we have with the hemiacetals. Okay, now want to write another mechanism, and that is that hemiacetal formation is reversible in acid or basic conditions. Acetal formation, including the formation of glycosides, is also reversible, but only in acid. Let's write out the mechanism for the reversal of the formation of the glycoside. All right, so what I'm talking about is reversal of acetal formation, right? And this can happen with any acetal, but since we're talking about carbohydrates right now, I want to talk about the mechanism about reversal of a sugar. All right, so let's start with something simple. Something like this. Okay, so is that an acetal? Yes. Did it come from a sugar? Yes. It's a glycoside. All right. So now, how do we reverse the equilibrium? Is that we add water and acid to the acetal. And when the acetal is exposed to water and acid, the acetal is going to fall apart. Okay, so this plus water plus acid, and now let's look at the products of this reaction. The acetal oxygens fall off as OH oxygens, and the acetal carbon reverts to a carbonyl carbon. So the product here is going to be the products are going to be these, right? So again, just to recap, what happened, when an acetal reacts with water and acid, the acetal oxygens fall off as OH oxygens. The acetal oxygens fell off as OH oxygens, and the acetal carbon reverts to a carbonyl carbon. Okay, So we could either leave it there, but I do want you to be aware that in solution, this thing is going to ring up into a hemiacetal. So this could get a little bit complicated. Let's go through this mechanism here. Okay, first step is going to be, we need steps that show how this molecule of methanol is produced. So our first step would be protonation of the oxygen atom that is outside of the ring. You could also start by protonating this one, but so it doesn't really matter. I can't write both of them. Let's just protonate this oxygen that's outside of the ring. That's easier to understand because we need to figure out how this molecule of methanol is produced. All right, first step, protonation of the oxygen atom, the acetal oxygen, of one of these acetal oxygens. And here again, this is a theme that we see repeatedly when we're writing mechanisms. Positively charged oxygen is not happy. Oxygen's too electronegative. It wants to be either neutral or negatively charged. The way it's going to become neutral is that it gobbles up the electrons in this bond that was holding it to the carbon atom. Okay, so now this molecule goes flying off, right? So there's our molecule of methanol that was produced, and what is left behind here is this thing. Okay, and so this is an electrophile. It's electron poor. Water, which is also present, now gets into the act, and it is going to function as the nucleophile. So nucleophile attacks electrophile. And you see how I snuck in that wavy line? Yeah, because this water molecule can attack from either the front or from the back. This is just an efficient, time-saving way of communicating that both the alpha and the beta force will be created here, depending on the direction of the attack of the water molecule. Oh, here we go again. Another positively charged oxygen. That doesn't like it. That doesn't like that positive charge. So it is going to gobble up the electron pair that is bonding it to one of these hydrogens. The base comes along, removes one of these protons in an acid-base reaction. Okay, going to try to finish down here. Hope it fits. Wavy, wavy, wavy. And what happened here was the proton was removed. Okay, and so now that oxygen has become neutral. But what is this? Oh, this is the hemiacetal, right? It's an carbon atom that is bonded to two oxygens, one of which is an OH oxygen, the other one is not. And we know that a hemiacetal under acidic conditions or even under basic conditions is in equilibrium with its carbonyl parent. So let's finish up this mechanism. Let's take this back to here, right? But I do want you to notice that the hemiacetal is involved in this equilibrium. All right, so what happens now is this proton that came flying off in the previous step now comes back into the picture, and the oxygen inside the ring is going to get protonated. We started this mechanism by protonating the oxygen outside the ring. Now we're going to finish up by protonating the oxygen inside the ring. And once again, we get a positively charged oxygen. And we've seen that a gazillion times already. Doesn't like to have that positive charge. How is it going to satisfy the positive charge? By breaking one of these bonds. So it's going to gobble up this electron pair. So now this is just OH dash 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 OME. And we get this carbocation intermediate. And I got rid of this wavy line because this is now a steric number of 3. This is not a chicken foot. This is not dashing and wedging. It's planar. Last step. Another deprotonation. A final deprotonation. And we're back to the open chain form of the sugar. Okay, and so those are the steps of the mechanism of the hydrolysis or of the reversal of the acetal formation. So how do you reverse this equilibrium? You add acid and water to the glycoside. Okay, so let's do some product prediction, shall we? Okay, so draw the structure of the products. So I'm just going for product prediction here. So if this is a real sugar, it would have all of this dashing and wedging. Let's not worry about that now. So predict the product. So when you're studying these mechanisms, studying these reactions, one of the things that you want to make sure that you understand is, what are you looking at? What is the recipe that you're looking at, right? Just like I have analogized this before. If I show you 2 pieces of bread, 3 strips of bacon, a slice of tomato, a leaf of lettuce, and a jar of mayonnaise, right? What are you going to put over here? What is that the recipe for? So when you're studying these reactions, you want to make sure that you know what you're looking at, because each of these reactions is following a certain recipe. Okay. That's an acetal. That's water and that's acid. That's the recipe for the hydrolysis or for the reversal of the acetal formation. And what happens? The acetal oxygens fall off as OH oxygens. The acetal carbon reverts to a carbonyl carbon. The acetal oxygens fall off as OH oxygens. The acetal oxygens fall off as OH oxygens. And the acetal carbon, I'm going to put a little dot on him, the acetal carbon reverts to a carbonyl carbon. Of course, there's a hydrogen here. There's been a hydrogen there all along, but just didn't write it because I'm using a bond line structure, but it's still there. Okay, and so this would be the open chain of that sugar. But this guy could ring up This guy could ring up to a hemiacetal. Okay, how'd that go? Let's try another one. Okay, predict the product there. Is it the recipe for the reversal of the acetal? Oh my heavens, yes. I see a carbon atom bonded to two oxygens, neither of which is an OH oxygen. That's an acetal. What happens when an acetal gets together with water and acid? The acetal oxygens fall off as OH oxygens, and the acetal carbon reverts to a carbonyl carbon. Okay, there's my acetal carbon. The acetal oxygens fall off as OH oxygens. Right? I'm drawing this in a hideously ugly way, but hoping to make it a little bit more understandable. Right? I'm not going for the beautiful little zigzag. The acetal carbon reverted to a carbonyl carbon. Okay, and so that would be the product of this acetal reversion. All right, so now I want to try to show you some pretty pictures. Let's see, that will be called screen sharing. Yes, I'm sharing that. Can you see that? Can anybody see this? That slide, yes?
Yes.
Okay, so what this slide is talking about is just a summary of a lot of the stuff that we have already talked about, is that carbohydrates exist as cyclic structures in aqueous solution, and this could be a glass of water or a beaker in a laboratory. It's also the inside of your cell. Okay, and so these are two big sugars here, glucose, that's huge for metabolism, and ribose, this is the carbohydrate residue in RNA, and let's look at this data. It can form pyranoses and furanoses. The major, and look how much open chain there is in solution, hardly any, right? Glucose mostly forms the beta pyranose. Ribose also mostly exists as a beta pyranose, but you have the furanoses, alpha and beta, all present in solution as well. Okay, so the dissolving a sugar in water, wow, that's complicated. All kinds of things can happen. Okay, and today we're talking about glycosides, which are sugar acetals. And Mother Nature and organic chemists have gone crazy making sugar acetals. They are everywhere in biochemistry and in organic chemistry, and believe it or not, in the real world. Okay, so this is salicin. This is a glycoside. It comes from willow, and I see right here, I see an acetal carbon, a carbon atom bonded to two oxygens, neither of which is OH oxygen. So this is an acetal. It's a glycoside, and I can see that it is the beta glycoside of a D sugar, which is glucose. Anyway, you know, it's been known for thousands of years. I don't know how people discovered this, but it has been known for thousands of years that if you cook birch or aspen bark, those are trees, if you cook birch or aspen bark in water and drink that liquid, it is a way of reducing fever and relieving pain. It's an analgesic. And some cavemen discovered that hundreds of thousands of years ago, but it was not until the 1800s that people realized what was in that birch bark tea that relieved pain and reduced fever. And it was this thing, salicin, this glycoside. And we're not too hot on drinking birch bark and aspen bark tea. So instead, the synthetic substitute is aspirin. And we see there's some kind of similarities between the salicin structure and the aspirin structure. Okay, so as I said before, Mother Nature and organic chemists have gone crazy making sugar acetals. So this is the essence of vanilla. And we see it's a glycoside. This is a molecule of glucose, and it is bonded by a glycosidic bond to a molecule of vanillin. Now, if you go to CVS or Walmart or a dollar store and buy vanilla, what you're getting is just this part of the molecule, and some alcohol, some very harsh, unappetizing flavor. But if you go to Williams Sonoma or maybe Whole Foods and buy their vanilla flavoring, you're getting something that tastes a lot better because the natural vanilla flavor is bonded to a glucose, to a sugar molecule. And so this tastes a whole lot better when you ingest this. The acetal falls apart into the vanillin and to this molecule of glucose, which has a sweet flavor. Okay, so now I want to stop sharing. I want to go back to here. And oh dear. Now what? Okay. So the recipe for the glycoside is the same as the recipe for any old acetal. But when we talk about a sugar, remember the definition of a sugar is a polyhydroxyaldehyde or ketone. That polyhydroxy means that you're going to have a lot of OH groups, more than one OH group in the sugar. So that a sugar not only demonstrates aldehyde and ketone reactivity, because sugars are aldehydes or ketones, but sugars also demonstrate alcohol reactivity because sugars are polyhydroxy. So in the examples that we've been talking about up to now, we've always started out with some kind of sugar. Started out with some kind of sugar, maybe looking like this, right? Some kind of sugar, maybe looking like this, and have reacted it with some kind of alcohol, maybe ethanol, acidic conditions. That's the recipe for the formation of acetal, right? We get something that looks like this. But this OH group, this could come from a second sugar molecule, because sugars, carbohydrates have both the aldehyde or ketone functionality as well as many alcohol functionalities. So there's nothing stopping us from using a second molecule of sugar, either different from this one or the same as this one, to make a new acetal. So I'll give you a simple example. So let's say we have something that looks like this. I'm drawing the hemiacetal form, and now react that with a molecule, a second molecule of sugar. I'm going to let this OH group attack. It's simply the recipe for an acetal, like something like that. And so this is going to form an acetal just like the previous example did. And so here what we're going to get is an acetal. I see, this hair is in the way, I see an acetal carbon. I see a carbon that's bonded to two oxygens, neither of which is an OH oxygen. Okay, this thing is an acetal that was formed by the union, by the coming together of two sugars. This is called a disaccharide. Right, and now the disaccharide, meaning two sugars, have come together to form this acetal. And notice this guy here, this carbon here, I'm going to put an asterisk on there. He could be alpha or beta. And then here's a hemiacetal over here, put another asterisk over here. He could be alpha or beta. So we have a lot of possibilities for all kinds of stereochemical intricacies. Okay, so now let me show you some more pretty pictures. Let's try a new share. Share. Sharing this. It says share computer sound. I thought I was doing that the whole time. Okay, so maybe you're interested in food chemistry, dietetics, nutrition, so on and so forth. Lactose, and you know a lot of people have problems with lactose. They are lactose intolerant. Lactose is a disaccharide. It is two sugar molecules, a galactose and a glucose molecule that got together, and lactose has this beta glycosidic bond, right? If we went through all of the stereochemistry of everything and dashing and wedging and R and S and everything like that, we'd see that at this carbon here, right here, that is that would be a beta linkage. So lactose is a beta, is a disaccharide that has a beta glycosidic linkage. So that's an example of a disaccharide. There's nothing stopping us. If two sugars can get together to form a disaccharide, there's nothing stopping us from getting three sugars together to form a trisaccharide, or four sugars, or five sugars, or many, many, many sugars. And so Mother Nature has gone crazy making these sugar acetals. And in fact, the most abundant organic compound on the surface of this planet is a polysaccharide called cellulose. So cellulose is a bunch of glucose molecules got together to form a linear polymer of glycosides. And what I'm illustrating here is just a tiny little section of the cellulose molecule. I see an acetal carbon right here. I see another acetal carbon over here. So cellulose is a polysaccharide where thousands and thousands and thousands of glucose molecules have gotten together, forming always these beta glycosidic linkages. And you know, cellulose, this is the most abundant organic compound on the surface of the earth, because vegetation, leaves, bark, the tissues of plants are made out of cellulose. And they're just bazillions and bazillions and bazillions of tons of cellulose in the natural world. If you want to look at some pure cellulose, that's cotton. Cotton is almost 100% pure cellulose. Paper is, upwards of 95, 99% cellulose. One of the very interesting things about cellulose is this beta-glycosidic bond. This cannot be digested by humans. We don't have the enzymes that can break up cellulose into its glucose constituents. Just think if we could, right? Wood, leaves, cotton, all of that is made out of cellulose. If you had the enzymes to digest cellulose, on your next date, you would be going to a restaurant and maybe ordering a t-shirt for dinner. Maybe your date would order a ream of copy paper as the entree, because if we had the enzymes to break up this beta-glycosidic bond in cellulose, we could eat cotton, we could eat wood, we could eat leaves, but we don't. Only bacteria have those enzymes. Even animals that are herbivores, like cows and deers, they don't have the enzymes to break down plant matter. Rather, it is microbes in their gut that break down all that plant matter for them. Okay, now if we string together a bunch of glucose molecules with a beta as a beta glycosides, we get cellulose, indigestible. But if we string together a bunch of glucose molecules with an alpha glycosidic bond, then we get starch. And human beings do have the enzymes to digest, to break apart this alpha glycosidic bond, but not the beta glycosidic bond. So see, starch is much smaller than cellulose. It's only about 200 glucose molecules strung together. And so, this is the dietary starch. So this is all pretty interesting, is that because enzymes are chiral, and because cellulose is loaded with chirality centers and it's chiral, and because starch is loaded with chirality centers and it's chiral, is that the enzymes are either selective for cellulose or they're selective for starch, but not the same enzyme for both of them. Okay. So here we're going to draw our traditional heavy double lines to represent the end of the material for exam number 3. Okay, so on Wednesday we'll have a lecture, but it will be on new stuff that is not going to be on the exam. So before we go, any questions about anything?
Yeah, I have a question. You mentioned that we were gonna have homework and top hat questions, but I haven't seen anything put up on Blackboard, so I just was...
Yeah, no, I thought that having a homework the same week as an exam was not going to be a very good idea, so we'll have homework after.
Okay, thank you. And also because you already discussed experiment 6 on the previous pre-lab, are we going to discuss experiment 7, and then are they both due this Friday, or?
Experiment 6 and experiment 7 will both be due Friday of next week.
Okay, yeah, because I didn't see them put up on Gradescope, so I was just...
Well, you're not looking for Gradescope for the form that you submit. You're looking for Blackboard.
But don't we submit it on like when it's done on Gradescope?
You submit it to Gradescope, but you don't go to Gradescope to download the thing you're supposed to submit.
Oh, yeah, okay, yeah. Thank
I
you.
just want to make sure that you understand that.
Yeah, I download the format.
The
Like
remote submission form from the lab website.
yeah.
Okay? Anything else before we go?
Oh, sorry. I also had one more thing that I was not able to download it like as a PDF, so I took pictures and
Download what?
the homework. So I took pictures of it,
There
and
hasn't been any homework.
I mean like the lab. I took
Okay.
pictures of the printed out lab form, and then I was able to upload it as a PDF, but as pictures, not as like scanned. Is that okay?
Did you upload it as a PDF?
Yes.
That's the only thing that matters. That should be the file format. You can't upload JPEGs or bitmaps or anything else.
Okay, thank you.
As long as you upload the PDF, that's fine. Anybody else? Okay. Have a good day. See you on Wednesday.